Hi everyone, my name is Sarah Rumeh and I am excited to kick off this presentation. I will start by introducing my talented teammates, Noura Sbehi, Ghaida Al-Malki, and Ghada Al-Mtiri. Together, we have developed an innovative solution we are proud to share with you today. Let's begin with a quick overview. Road infrastructure is critical for transportation and public safety, especially in fast-growing regions like Saudi Arabia. Unfortunately, as cities expand, issues like potholes on roads become a significant risk to drivers and pedestrians alike. To address this, we created Jadda, an AI-powered system designed to revolutionize how we detect and manage road defects. Using advanced computer vision and machine learning, Jadda automates the process of identifying road issues. Unlike traditional inspection methods, which can be slow and prone to human error, Jadda is fast, precise, and user-friendly, also enabling quicker maintenance and improving road safety for everyone. At its core, Jadda uses high-resolution image datasets and the YOLO V8 SIG model to detect defects accurately. By doing so, we aim to bring smarter road management and greater safety to urban areas across Saudi Arabia. Now, let's take a closer look at the key challenges we identified. 1. Efficiency issue. Traditional road inspections are time-consuming and labor-intensive. 2. Safety risks. Delays in identifying defects like potholes can lead to accidents. 3. Human error. Inspectors may overlook or misclassify defects. 4. Maintenance challenges. Inconsistent inspections make it harder to plan proactive repairs. 5. Need for automation. Growing urban populations require faster automated solutions to ensure safer roads. And this brings us to our solution, Jadda, a system designed to address these challenges. Thank you, and now I will hand it over to my friend Ghada for more details.
During our data collection journey, we focused on gathering high-resolution data for various road conditions to create a comprehensive dataset. The data was collected from open sources that publish images specifically for road defects. Also, open data was obtained from ministries and authorities, and manual data collection was also conducted. Our data consists of 6 classes, which can be categorized as manholes, open manholes, unmarked bump, speed bump, and pothole. The data was collected effectively to enable the model to recognize and classify these defects effectively and with greater accuracy. And now I'll let you with Ghaida to explain the model implementation.
Now let's dive into the model implementation, the core of our research. For this study, we used YOLO V8 segment, an instant segmentation model. YOLO V8 segment is a significant upgrade in the YOLO series, taking object detection to the next level. Unlike earlier versions that relied on bounding boxes, this model adds a segmentation branch, allowing it to outline objects at the pixel level. For road defects, this means precise shape detection, not just location. By fine-tuning YOLO V8 segment for these specific defects, the model delivers detailed insight, enabling road maintenance to becoming faster, smarter, and more effective. Now, let's take a closer look at the architecture of YOLO V8 segment. It's designed with 3 key components, each playing a crucial role in enabling detection and segmentation tasks. These components are the backbone, the neck, and the head. First, on the left, we have the backbone. Think of the backbone as the model's feature extractor. Its job is to process the input image of the road surface and identifying key patterns such as edges and texture. A major strength of the backbone lays in its C2F modules. These are specialized bottleneck layers that enhance the efficiency of feature extraction. The C2F module works by splitting the input into two branches. One branch is further processed through additional layers, while the other bypasses them. This dual approach ensures that the model retains both the original and transformed information, improving its ability to recognize complex patterns. Additionally, the backbone incorporates an SBBF layer. This layer is responsible for capturing multi-scale features. It enables the model to detect defects of varying sizes in a single pass. For example, whether it's a small or a large pothole, the backbone captures both fine details and the overall structure. Next, in the middle, we have the neck. The neck's job is to take the features extracted by the backbone and refine them, preparing them for the final predictions. It aggregates information from different sources to ensure both fine details and broader patterns are preserved. Here, the C2F modules makes another appearance. By refining the feature representation, they allow the model to better understand the boundaries and shapes of road defects. This step is especially important for distinguishing closely located defects, ensuring that overlapping or nearby defects are correctly segmented. Finally, on the right is the head. This is where all the refined features come together to generate the outputs. The head in ULV8 is highly flexible and can handle both classification and segmentation tasks. For this project, where segmentation is our focus, the head produces three outputs. One, bounding boxes, which locate and size each detected defect. Two, class scores, which indicate the likelihood of each defect belongs to a specific category, such as pothole. Three, and the most importantly, segmentation mask, which assign a label to every pixel in the image. The segmentation masks are what allow us to precisely outline the shape of each defect. This is crucial for instance segmentation, where individual defects are separated even if they belong to the same class. Together, these three components, the backbone, the neck, and the head, enables ULV8 segment to perform fast and accurate detection and segmentation, even in a complex environment. Training the model involved working with a dataset of high-resolution road images labeled with defects. Over 50 epochs, we optimized the model for accuracy and efficiency. The result is a precise and fast model that's ready for real-world challenges. With YOLO VA segment, we now have a powerful tool to enhance road maintenance operations, allowing for quicker interventions and safer roads. And with that, this concludes the model implementation section. I'll hand it over to Noura to take you through the next part. Thank you.
Let me ask you something. Have you ever driving on a road and wondered if there is a system that could be reliable, detecting the hazard like open manhole or speed bump before you encounter them? Now, imagine if such a system that had to decide how confident it about what it sees, what if it was wrong? This is where the preceding confidence curve comes into place. Look closely at these lines. Each one represents a different defect type, manholes, speed bump, holes, and so on. Can you see how they consistently stay close to the top, even as a confident various? That's what makes this model stand out. It is not just good when it is sure, it is good all the time. Now, here's the exciting part about this model. Even when the model is working with a low confidence level, it is still maintaining a high precision. Why this is important? Well, let's say you're in a scenario where the lighting is poor or there is a heavy traffic and the model is this confident. We don't want to sadly starting giving you a wrong detections, right? This curve is showing that is want. Okay guys, let's make it real.
Imagine a city maintenance team using this system. If the model sent to them 100 defect alerts, they would want as many of this as possible to be accurate, because responding to this false alert waste of time and money. This curve proved that the system avoid the false positive even when it's work under tough conditions. Going to the next slide. In this curve, let me ask you something. What is more important in detection system, catching all the defects or being sure every defect is correct? It is tough balance, right? That exactly what precision recall curve help us to understand. Okay guys, to explain this model, we need to break down the concepts. First of all, we have the precision. This is to tell us how accurate the detection are. For example, if the model says it found a butthole, how often is actually a butthole? We need to answer this question by this curve. Recall, this is measure how many of the actual defect the model managed to detect. Did it find everything it was supposed to? All this question is answered by this curve. Okay, let's look to the graph. Each line represents a different defect type: manhole, speed bump, open manhole, and so on. Notice how the curves stay high before debugging. This is a good sign. It shows the model achieves a high precision and recall for the most defects. Can you spot the open manhole curve? It is one of the top performance defect type with the highest balance. This is critical because open manhole are measure a safety risk. The model ensures this rarely missed while keeping a false positive low. Okay, the all classes curve represented by the blue line show how the model performance overall. It is consistently maintains a strong balance across all defect type. This means that whether it is hole, a speed bump, or unmarked defect, the model is reliable and effective. On this curve, I have a question for you. Have you ever noticed how something that rarest problem are the most dangerous one? Think of the open manhole or tiny buttholes. May not be common, but missing them could have serious consequences. Now, how do we teach the model to pay attention to this rare defect while still performance well on the common ones? This is where the focal loss comes in. It is a technique designed to address the challenging of the class's imbalance. It is teach the model to focus more on learning from the rarer and the harder to detect defects. Now, let's look to the learning curve. Okay, in the curve we have two lines, the blue one and the red one. The blue one is represent the training loss. This is represent the model learning progress during the training. Notice how it is steadily decrease over the epoch. That sign the model is getting better at identifying defects, even the rarest one. On the other one, the red line, validation loss. This is track how well the model performance on unseen data. The study decline here tells us the model isn't just memorizing the training data, it is actually learning to generalize it. Now, why is this important? Because rare defects like open manholes, unmarked bump, and so on could easily be overlooked. By minimizing the focal loss, the model becomes more balanced. It learns to detect not just the obvious defect, but also the critical one that occur less frequently. Let's imagine if the system were deployed in your city. You wouldn't want to miss small potholes that could damage your car, right? This curve reassures us that the model is beginning training to catch both common and rare hazard effectively. In the converging matrix, we all focus about the mistakes. For example, have you ever used GPS and it gets your location slightly wrong? that mistake in a prediction, and understanding those mistakes, it's what the converging matrix all about. Let's dive in to see how this is applied in our road defect detection model. We have two matrices. The first one is row converging matrix, the left one. This is matrix show the actual number of predictions made by the model. Each box represents how many times the model classified a defect correctly or incorrectly. Example, for instance, the model identify 118 open manhole correctly, but look here, it is also confused some manholes with other defect type. The other one is normalized converging matrix, the right one. Now, this is matrix give us a properties instead of row count. It is answer a question like, out of all defects that were are truly manholes, how many did the model correctly classifies? Example, you can see the model has a highly accurate for open manholes. It is give us 0.94, but there is a subtle drop of the unmarked bump. It is 0.84. Now, why does this matter? Imagine a road maintenance team relying on these predictions. If the model mixed up the potholes and speed bump, the team might be respond to the wrong defect, wasting the time and resources. By analyzing this matrix, we can pinpoint and addresses these challenges. Let's look at the background categories. Notice the lighter shading. That means the model is very good at distinguishing defect from non-defecting areas. This is critical because it is ensure the model is focused only on the real root hazard. Now we have the validation performance matrix accuracies. Let's talk about the grade. Imagine your model is a student beginning graded not just in one subject but in several, like precision, recall, MAP resources, and so on. These metrics are like a detailed report card showing how well our model has performed. So, how did the yellow V8 segmentation model do? Let's go in details. First of all, we have MAP 50. This matrix measures the model ability to detect and localize the defect with a high accuracy at 50% intersections over onion threshold. Think of it as the model scoring ahead if it is detection overlap with the actual defect by at least 50%. The overall MAP 50 score of 0.878 showing the model performance will across all the defect type. The other one we have MAP 5095. This is together test the averaging the precision across a range of IOU threshold from 50% to 95%. It is like moving from easy quizzes to the final exams. The score of 0.705 determined that the model handled even the most challenging detections task is reliable. The third one we have precision and recall. Precision tells us how many of the defects detected by the model were actually correct, while recall showing how many of the real defects the model successfully found. The model maintains strong precision and recall scoring across all defect type, proving its reliabilities. In conclusion, this validation table proves that the yellow V8 segmentation model is not just good, it is ready for the actions, with a high precision, strong balance for the matrix. It is perfect tool for the road safety and maintenance. This is the sample of our model result. This result is highlighting the model exponential adaptabilities and the precision, transforming the way road maintenance is managed. By accurately detecting the hazards of all sizes and in diverse environment, the model empower productive interventions enhancement public safety and set a new standard of intelligence infrastructure management.
Due to the limitations in our project's data collection methods, we aim to improve the data collection process in our project and make it more efficient than manual collection. We also working on enabling the model to recognize various road conditions, not just the 6 classes we mentioned. Upcoming addition include sidewalks and cracks. Furthermore, we plan to implement artificial intelligence algorithm to assist in predictions, helping us forecast emerging issues and defects. The JADA project utilized the advanced instance segmentation model YOLO V8 to detect road defects such as potholes and open manholes. By fine-tuning this model, it is able to be accurately identify and segment these defects, improving road safety and infrastructure management. This innovative approach demonstrates the power of AI in solving real-world challenges. The project emphasized the transformative impact of AI in enhancing infrastructure maintenance and ensuring safer public spaces. We hope for this project to have an impact on road safety by facilitating operations and improving the quality of work related to road damage. We appreciate your valuable time and thank you for listening.